Hello students. In this video I'm going to show you how to write equations for forces in 2 dimensions, and then also how to deal with vector component forces and a little bit about the force of friction. So I have a diagram from the textbook of a person pulling a child on a sled across the ground. The rope makes an angle of 30 degrees. The child and the sled are surrounded by this dashed orange line. That represents the fact that they're a system together that we're interested in. We could call it the child sled system. So I went ahead and drew a free body diagram for this child sled system with the force of the ground upward, the force of the rope at about 30 degrees, the force of the earth straight downward, and the force of kinetic friction to the left. So first thing I'll do is I will create a sum of the forces diagram. And I'm going to do sum of the forces equation. I'm going to do one for each dimension. So you've seen me write sum of the forces like this with a vector symbol. When I write that, then we can add any two forces together, and we would put a, um, an addition symbol, a plus sign, to show that we're adding them together. This does not necessarily mean that we are summing them. We might be adding the opposite of one if they are in opposite directions. So that this plus sign might turn into a minus sign later when we go about trying to solve this equation. We say, oh, the sum of the forces is equal to force 1, which is positive, and force 2 is negative. So this is a vector statement, and this is a scalar statement. I took off the vector symbols and I went ahead and put in the minus sign representing the fact that the direction of force 2 is in a negative direction, perhaps left. So let's go ahead and write a specific equation for for this force diagram, this free body diagram, and let's write it in 2 dimensions, and let's skip the vector statement. And let's do, well, I'll show you the difference between the vector and the scalar statement. So if I write the vector statement, I could write this. The sum of the forces is equal to the force of the ground. You never want to write for F sub g for ground, because a lot of times people would take that to mean gravity, plus the force of the rope, and I'm just sort of going around my diagram, plus the force of earth, plus the force of friction. And that's, remember, the K stands for kinetic sliding friction. So that's a correct statement. I've got those 4 forces on my free body diagram, but it's not very easy to solve this statement. The way we would solve this likely would be a vector diagram. And I don't want to do that right now. I want to show you an analytical approach using math. So I'm going to remove that. It's correct, but notice I'm not just adding these things like I would add numbers, because they're all in different directions. So I'd have to take that into account into my mathematics. And once again, the way to do that is typically with a vector tip to tail diagram. So I'm going to remove that, and I'm going to write the scalar statement for each dimension. So the sum of the forces in the x symbolizes the horizontal forces, and that would equal force of rope, the x component, only the horizontal part of it, minus the force of sliding friction, kinetic friction. I could replace sigma f with ma. I often put an x there to symbolize it's a horizontal acceleration. So then this symbolizes the net force. It's the formula for calculating the net force in the horizontal dimension, and that would equal the force of the rope in the horizontal dimension minus the force of sliding kinetic friction. For the y, for the vertical, sigma Fy, so the sum of the vertical forces, the forces in the y dimension, that I know would equal 0 for a person pulling a child sled system across level ground. because the child sled system is not accelerating up or down, so they must equal 0. So then, same process, force of ground, positive because it's upward, plus force of rope has a vertical component that's upward. I'll put a y there to symbolize that, minus the force of the earth, which I can see from my diagram is downward. So I'm ready to solve either of these two equations for whatever the question might ask for. If it's asking for acceleration, then I could plug in numbers and rearrange this top equation for acceleration. If it's asking for, say, the force of the ground on the object, on the child sled system, I could rearrange this equation mathematically for the force of the ground and plug in the numbers. But I don't actually know what the component forces are until I calculate those. So sometimes it's useful to go ahead and do that. When we do that, we draw a separate diagram like this, and we give the components some distinguishing characteristic. I'll make them red and I'll draw them as dashed vectors. They're not really there. We are imagining that we could get the effect of pulling the rope with this force, whatever force the person is applying at 30 degrees, by also pulling straight right and pulling straight up in two separate pulls. So this is our horizontal and this is our vertical component. Often we just write X and Y to symbolize those. Theta is 30 degrees. It's kind of a lousy theta, but there you go. And notice that Y is the opposite and X is the adjacent side for the little right triangle I constructed. So you could write something like cosine of 30 degrees must equal force of rope, or pardon me, X, my bad, X over force of rope. So then X equals force of rope cosine 30 degrees. And then we could do the same thing for Y. Sine of 30 degrees equals Y over force of rope. And then Y equals force of rope multiplied by the sine of 30 degrees. So that would be the way to set up all of the equations that you might need to solve a problem like this. Um, oh, um, sorry, I'm looking at my screen. My handwriting is a little messy. Let me clean this up. There are many places it's messy, but that does not look like a 30 degrees. Now, the last thing I want to mention is that when you're calculating the force of friction, remember that you can calculate the force of friction, whether it's kinetic or static, by using force of friction is equal to mu times whatever the normal force is, where normal force stands for perpendicular surface force, and I typically call that the force of surface rather than normal force. But I'm mentioning the term normal force because I believe the textbook uses it and it's in Mastering Physics. So that's synonymous with what I've been calling normal force. So you would need to, in this situation, before you could find the force of friction here, you would need to find the normal force, the force of the ground, here. So what I would do is begin with the y equation. First step is always to draw the free body diagram, label all the forces, construct your sum of the forces in the x and your sum of the forces in the y statements with no numbers, just symbols, and then think for a minute about what the next step is based on what is given in the problem. A typical thing to do would be to go ahead and find component forces and then to find the surface force if other numbers are given. But it all depends on the problem. I can do some specific problems. If you have a question about it, let me know. Thanks for watching, and remember, what one fool can learn, another can.